These are the notes for AP Calculus on the topic of continuity. So continuity is where a function is continuous. So let's look at the definition for continuity at a point. So first, look at the left-hand side of this equation. It says the limit as x approaches c of f of x. So what that implies, because that's the general limit, that implies that the left-hand and right-hand limits must be equal for that general limit to equal something, for it to exist. So, we sketch what this would look like. C just represents some specific x value, and if we know that the general limit exists, the left and right-hand limits must be the same. So, from the left and from the right is approaching the same y value there. I drew an open circle because just because it approaches that value doesn't mean it actually gets to that value. It could, but not necessarily. And that's where this other part of the equation comes into play. It says this equals f of c. Well, f of c represents the y-coordinate at that point. So when x is c, when you plug that in there into the function, you get the same y-coordinate so that it equals the limit. That would make sure that it's actually not a hole, that it's filled in there. So if the general limit exists and that's where the y value is, that's the definition of being continuous at a point. Now let's look at some different types of discontinuities, things that make the function discontinuous. So one example is a hole. That means it's not all connected. So discontinuous is anything that makes the function not all connected and continuous. Another thing that can make the function discontinuous, another type of discontinuity, is vertical asymptotes. If you have a vertical asymptote, when the function goes up to infinity or down to negative infinity and it's not connected. Another thing that can make the function discontinuous is breakpoints of piecewise functions, where from the left and from the right not approaching the same thing. So breakpoints of piecewise functions. And finally, another thing that can make function discontinuous is even roots. Like square roots, fourth roots, sixth roots. So even roots, remember, like those dangerous radical problems, that means that on one side it's imaginary, so it's not all connected, it makes it discontinuous, it makes the function end essentially. All right, now that we've looked at some discontinuities, let's look at how we would write the intervals on which f is continuous. So before we do that, let's take a look at the domain, because the way we write our intervals that are continuous is similar to how we write the domain. And then we go from left to right, and that we use the x values. So let's start with the domain, and then we'll compare that to the intervals on which f is continuous. So here's the domain. Our domain moving from left to right, the lowest x value this reaches, you can see, is -7. And that's included because it's got a closed point, a regular point, so that's with a bracket. And then the first place we don't have something in the domain, notice we don't have to stop at -3 because there's a point right there, there's a closed circle. But if you take a look at 2, where there's a hole, there is no point anywhere else. So you would have to stop at 2 with a parentheses because it's not included. And then a U for union for the next interval. The next interval resumes right after 2 with parentheses because it's got an open circle. We don't have to stop at 3 for the domain because there is a closed point there. It is in the domain because of that point. And we keep on going, then we hit the vertical asymptote at 6. So you always have to stop at the vertical asymptotes because the function's undefined there. And then union with the next interval, so resumes right after 6 with the parentheses. And then we have a hole at 8, but we don't have to stop there because if we look at the point down here, that point means there actually is a y value there. So 8 is in the domain, and then it goes right forever, so all the way to infinity. Now let's compare that with the intervals on which f is continuous. So we can say f of x is continuous on We still move from left to right like the domain. We're still using the x values, but the difference is every time we hit a place where the function is not connected, where it's not continuous, we have to stop the interval. So we can still start at -7 with a bracket. This included. But notice the first place is not continuous is at x equals -3. And it's an open circle, so we use a parentheses. And then union. Notice that first continuous interval covers this section of the graph right here. Then it starts right here at -3, but this is a closed circle, so that's included. So I'll do bracket -3. And the next discontinuity we hit is the hole right there at 2, at x equals 2. So 2 with a parentheses, not included. So that covers the interval from there to there. And then it resumes right after 2 with a parentheses, open circle. And then it stops at 3 with a bracket, closed circle. And then union. Then it starts at 3 with an open circle, so parentheses. And then it goes to the vertical asymptote at 6 with a parentheses. Then union. Then it goes from 6 with a parentheses. There's a hole at 8 with a parentheses. And then we have this point all by itself here. Now that means it's in the 8 is in the domain. However, we're looking at the intervals on which f is continuous. And a point by itself is not considered an interval, so we skip that. And then we go from 8 with parentheses. You can see it goes right forever all the way to infinity. Okay. So notice the domain and continuous intervals are similar, but they're not exactly the same because we have to stop more often on the continuous intervals because every time it's discontinuous we have to stop, whether or not it's in the domain. Okay, now let's take a look at some piecewise functions and find some different information about them. So let's start with a piecewise function where this first piece applies everywhere except for 3, if x does not equal 3, and this piece applies only when x equals 3. So it says find the left, right, and general limits at the breakpoints. Well, on this type of piecewise function, because this applies everywhere but 3, it applies on both sides of 3, we can start with the general limit. So the limit as x approaches 3 of g of x. First thing you do is substitute in 3. See what's happening? So we have 2 minus the square root of 3 plus 1 over 3 squared minus 9. Now the square root of 3 plus 1, that's the square root of 4 is 2, so we have 2 minus 2, that's 0, over 3 squared is 9, minus 9 gives you 0. Remember, 0 over 0 indicates we have a hole at x equals 3. Meaning to get rid of that hole, we need to cancel the factor x minus 3. So the way we can do that, I'll get this piece right down here and rewrite it. Because we have radicals on the numerator, there's 2 terms. The way to get rid of the radical so that we can eventually cancel the x minus 3 is to multiply by the conjugate. The conjugate of 2 minus the square root of x plus 1 is 2 plus the square root of x plus 1. Remember, you just change the sign in the middle. Everything else stays the same. But to balance it out algebraically, you also have to multiply the denominator by the same thing. So 2 plus the square root of x plus 1. Now let's go ahead and multiply out the numerator. So 2 times 2 gives you 4. And because they're conjugates, remember we don't have to multiply the outside terms and inside terms. So it would be 2 squared of x plus 1 and negative 2 squared of x plus 1, which would cancel out. And that always happens with conjugates. And then we have negative square root of x plus 1 times a positive square root of x plus 1. So negative times a positive is negative. And then the square root of x plus 1 times the square root of x plus 1, square roots cancel out. So we would have x plus 1, but make sure you put it in parentheses, because that negative out in front applies to the whole thing, even though the square root goes away. But on the denominator, we do not want to distribute that out, because our goal is to cancel the x minus 3, remember? So we want to instead factor this using difference of perfect squares. That would factor into x minus 3 and x plus 3. And let's leave the other factor on the denominator as 2 plus the square root of x plus 1. Then let's go ahead and keep simplifying the numerator. So if we distribute out the negative here, that's going to make it negative x and minus 1. And then if we combine it with the 4 minus 1 gives you 3 minus x. And then in order to get that to cancel out with the x minus 3, you can factor out a negative 1. So it becomes a positive x and a negative 3. So now we can cancel out, reduce the x minus 3s, reduce that to be 1. And then all that's left on the numerator is this negative that we factored out there, so negative 1. Over on the denominator, now we can substitute in, we remove the whole, now we can substitute in 3. And we'll no longer get 0 over 0. So it'll be 3 plus 3, and then times 2 plus the square root of 3 plus 1. So we have negative 1 over 3 plus 3 is 6 times, that's the square root of 4 is 2 plus 2 gives you 4. So we get negative 1 over 6 times 4 is 24. So negative 1/24, that's the general limit. So I'll write that up here. So now we know the limit as x approaches 3 of g of x equals negative 1/24. Now since that's the general limit, it's not really necessary to write down the left and right hand limits, because if the general limit is negative 1/24, then that implies that the left and right hand limits must also be negative 1/24. Now let's see what this looks like graphically to see if it's continuous or not, because that's what we're asked about next. In the second part it says determine if the function is continuous at each of the breakpoints. So the breakpoint here is 3, so let's figure out if it's continuous or not. Well, let's sketch a little graph so we can see what's happening. So over here at 3, so we just figured out the general limit is negative 1/24. And we know there's a hole there. So a little bit below 0, we've got a hole, the function's approaching that from both sides. To see if it's continuous, we have to take a look at this piece. Because this is the piece that applies only at x equals 3. So that just creates a point. It says when you plug in x equals 3, you get 4. So the point is actually up here at 3, 4. And now you can see, since that point did not fill in the hole, this function is not continuous at x equals 3. So we can say g of x, or actually you can just abbreviate it as g, is not continuous at x equals 3. That answers the second part, second thing we're asked to find. The only way this could be continuous is if these two are equal. So if this had been negative 1/24, then the point would have filled in the hole and making it continuous. Or if our general limit had been 4, then that point would have filled in the hole. So you're comparing the general limit with the point. If they're the same, it fills it in, it's continuous. If they're not the same, it doesn't fill in the hole and it's not continuous. All right, last thing we're going to look at is, for this problem, is find the limits as x approaches infinity and negative infinity. So now let's take a look at how we do that with piecewise functions. So it doesn't matter which one you start with. Say we start with a limit as x approaches infinity. So in this case, since this piece only applies at x equals 3, and this piece applies on both sides of 3, we use this top piece for both infinity and negative infinity. So let's look at the numerator, what would matter. When you plug in infinity, the 2's are going to be negligible, it's just going to be negative square root of x over the denominator, what's going to matter is infinity squared. Now you might be able to tell what that is going to be already. Square root of infinity over infinity squared, or if you're not sure, you can always use the exponents here. Square root of infinity is the same as infinity to the 1/2, and that's a square root, that's a 1. And infinity squared, if you get a common number, multiplied by 2 over 2 is the same as 4 over 2. And then you can reduce the infinity to 1/2 is a smaller, we cancel out, and now leave you with 3/2. So you have negative 1 over infinity to 3x. So there'd be a negative 1 over some huge number. So what that's really, really close to is 0. Remember, whenever you have infinities left over on the denominator when we simplify it, that's going to be 0. Now let's take a look at the limit as x approaches positive infinity. Sorry, negative infinity. Again, we're going to use the top piece here because this applies on both sides of 3. This only applies right at 3. So on the numerator, what's going to matter again is the negative square root. This time we're plugging in negative infinity over negative infinity squared. So you might think it's going to be just like infinity. However, what you have to notice is we've got an even root there, a square root. And this negative infinity means you're putting a negative inside of the square root instead of the even root. So that's going to be imaginary, so that tells us that this limit does not exist. Now let's take a look at the other major type of piecewise function. And that's when you have inequality signs instead of the equal to and the not equal to. So on this one, we're going to do the same thing, except we've got 2 breakpoints, -1 and 6. So let's say we start with the breakpoint of -1. On this one, on this type of piecewise function, you cannot start with a general limit at the breakpoints because you have different pieces of the function applying on either side of -1 and on either side of 6, the breakpoints. So here's where you have to start. On these type of piecewise functions, you always have to start with the left and right hand limits first. So let's look at the limit as x approaches -1 from the left of f of x. So the left of -1, you'd use the top piece. This says x is less than -1, so that'd be 2 times -1 plus 6 over -1 squared minus 9. So 2 times -1 is -2 plus 6 gives you 4 over -1 squared is 1 minus 9, -8. And 4 divided by -8 is -1/2. So the limit as x approaches -1 from the left is -1/2. And what we have to do is compare this to the limit as x approaches -1 from the right and see if they're the same or not. So let's find the limit as x approaches -1 from the right of f of x. So to the immediate right of -1, you can see that would be the middle piece there. So that would be 2 times -1 minus 6 over -1 minus 4. Which gives you 2 times -1 is -2, minus 6 is -8, over -1 minus 4 is -5, -8 divided by -5 is 8/5. The negatives reduce out. So we can see it from the left and the right, those are not the same. So if they're not the same, that tells us 2 things. First, it tells us that the general limit as x approaches -1 f of x does not exist. Because in order for the general limit to exist, remember, the left and right hand limits have to be equal. So they're not equal, so that doesn't exist. And the other thing it tells us is since the left and right hand limits are not equal, the function does not meet up at -1. So that means f is not continuous at x equals -1, because the left and right hand limits are not equal. In order to connect, these would have to be equal. You have to be approaching the same thing from both sides. So that answers all the questions we were asked about at that breakpoint. Now, let's figure out the same things at our other breakpoint of 6. So let's find the limit as x approaches 6 from the left. For 6 from the left, you'd use the middle piece. So do 2 times 6 minus 6 over 6 minus 4. 2 times 6 is 12, minus 6 gives you 6 over 6 minus 4 is 2, and 6 divided by 2 is 3. So the limit as x approaches 6 from the left is 3. Now let's find the limit as x approaches 6 from the right. So as x approaches 6 from the right, you use the bottom piece because this is where x is greater than 6. So if you substitute 6 in there, we get the square root of 9, which is 3. So this time, notice the left and right hand limits are equal, which means the general limit would also be 3 since those are equal. So the general limit as x approaches 6 f of x equals 3. That's one thing it tells us. But remember, it also tells us at that breakpoint, since the left and right limits are both 3, the function actually does meet up and is continuous. As long as, if we look back here, as long as one of these has an equal to, and there's an actual point. If neither one is equal to, then we would still end up with an open circle there. As long as one has the or equal to, in this case the middle piece, then it is going to be continuous. So I can say f is continuous on would be for an interval at x equals 6. And finally on this one, let's take a look at the limits at infinity and negative infinity. So the limit as x approaches infinity, f of x. So as x approaches infinity, you gotta look at your intervals and see where infinity fits. Infinity is greater than 6, so you use the bottom piece here. So that'd be the square root of the infinity. The 3 is going to be negligible. There's no denominator, so that's just going to approach infinity. So you get bigger and bigger. Even though the square slows it down, it still gets bigger and bigger forever. Now let's find the limit as x approaches negative infinity. So as x approaches negative infinity, the piece you would use would be the top piece, because negative infinity is less than negative 1. So in the numerator, what's going to matter, the term with the highest exponent is going to be 2 times negative infinity. And on the denominator, what's going to matter is that x squared, so negative infinity squared. So we can see one of the negative infinities cancels out, and we're left with 2 over negative infinity. And again, when you have infinities left on the denominator, that's 2 over some huge negative number. That's really, really close to 0. So whenever you have infinities left on the denominator, your limit's going to be 0. Okay, let's take a look at some other problems that are worded slightly differently. They're asking something similar though. It says, determine if g is continuous or not at x equals 1. And then it also asks you to justify your answer. Okay? So this is one of those inequality piecewise functions. So these are the ones where you have to find the left and right hand limits separately. So the limit as x approaches 1 from the left of g of x. Let's see what that is. From the left of 1, you'd use the top piece because that's the left where x is less than 1. So that'd be the natural log of 1 plus the cosine. When you plug in 1 there, 1 minus 1 is 0. Cosine is 0. And then the natural log of 1, remember that's just saying e to what exponent, because the natural log is 1 log base e equals 1. And e to what exponent equals 1, that's to the 0. So that would be 0 plus the cosine of 0. The 0 on the unit circle is right there, and cosine is the x coordinate, which is 1. So 0 plus 1 gives you 1. So that's our left-hand limit. Now let's find the limit as x approaches 1 to the right. As x approaches 1 from the right, we'd have e to the 1 minus 1 would be 0, plus 2 times the sine. When you substitute 1 for x there, it just becomes the sine of pi. So e to the 0 is 1, plus 2 times sine of pi, right over here. Remember, sine is the y coordinate, so that's 2 times 0, gives you 0 plus 1 is 1. So notice the left-hand and right-hand limits are the same, and one of them has the equal to, so that makes g continuous at x equals 1. So we first write down what we know. G is continuous at x equals 1. And then you write your justification, since or because. And then the reason why we know this is since the limit as x approaches 1 from the left of g of x equals the limit as x approaches 1 from the right of g of x. We just found the left-hand limits are equal. But we also have to mention, not only assume, that means there still could be a hole potentially, but because it's got the equal to right there, we know it's not a hole. So, by the definition of continuity at a point, put it back here, The left and right hand limits being equal only guarantees that the general limit will exist. But we still have to show that this equals the y-coordinate, so we need that in our justification as well. So we can just add on here, equals the y-coordinate at 1 would just be written as g of 1. Now let's look at the other type of piecewise function, where it has a does not equal to and equal to. And it says determine if h is continuous or not at x equals 2 and justify your answer. So this time, remember, we instead of starting with the left and right hand limits, because this applies on both sides of 2, we use the general limit. So the limit as x approaches 2 of h of x. Again, first thing you do is substitute in 2. So you get 2 squared minus 8 times 2 plus 12 over 4 minus 2 squared. So we have 4 plus 12 is 16 minus 16 is 0 over 4 minus 2 squared is 4 also gives you 0. So then in case we have a hole at x equals 2. That means we need to cancel x minus 2. So to do that, let's go ahead and factor this. If we factor out the numerator, that would be x minus 2 and x minus 6. And the denominator factors into 2 minus x and 2 plus x using difference of perfect squares. Then to get the x minus 2's to cancel, you just factor out a negative 1 out of one of them. So I'll factor out this one. So you have x minus 2. It's the negative x, positive x, and the positive 2, negative 2. So that way we can remove the hole by reducing those. And as soon as we remove the hole, now we can plug in 2. So in the numerator, that will give us 2 minus 6. On the number, we don't forget we've got this negative sign, and then we've got 2 plus 2. So that gives us 2 minus 6 is negative 4 over, that's 4, and the negative on the side, negative 4 gives you 1. So that's where the hole is at. But remember, we also have this point right here. We have to compare it to this. And notice this one is not the same as a 3 right there. So that point does not fill in the hole. What it would look like here would be 2. So x equals 2. The hole, or the limit is, general limit is 1, we just found. So from both sides, from the left and the right, it's approaching 1. The hole there. But the point right here, at 2, it does not fill it in because it's up here at 3. So because it doesn't fill in the hole, it's not continuous at 1. If it did, if this had been 1 right here, or if this had been 3 and they'd been equal, then it would be continuous. But here it's not. So we can say h is not continuous at x equals 2. And then your justification would be since, so to justify our answer. Here the reason why is because since the general limit we found, the limit as h approaches 2, sorry, x approaches 2 of h of x, this time it did not equal h of 2. Alright, let's take a look at a different type of piecewise problem here. This one says find the value of a so the function is continuous on negative infinity to infinity. So, because this would just be, if it was by itself, this would just be a parabola, and this one would just be a cubic graph. Separately, these two are continuous functions. And what it should say here is that a is a constant that we're solving for in this case. So the only place this piecewise function might not be continuous is at the breakpoint of -2. In order for it to be continuous, remember, like we saw here, the left and right-hand limits at the breakpoint would have to be equal. That would make it continuous. So that's what we're going to do in this case. Rather than find the left and right-hand limits, we're going to set them equal to each other to force it to be continuous. So it'd be the limit as x approaches -2 from the left, h of x, equals the limit as x approaches -2 from the right of h of x. So as x approaches -2 from the left, you would use the top piece. That's where x is less than -2 to the left of it. So substitute 2 into that piece, so it'll be 2 -2 squared minus a equals the limit as x approaches -2 from the right would be the bottom piece. That's where x is greater than -2, so it'd be a times -2 cubed plus 3 times -2. Remember, we're just substituting -2 for x, not for a. And then if we simplify that, -2 squared is 4 times 2 is 8 minus a. -2 cubed is -8 times a is -8a. And then 3 times -2 is -6. Then you get all the a's on one side if you add the a, or actually this would be the other one. If you add the 8a, the a is on the left side, subtract the 8, get the terms that don't have a on the right side. You get -a plus 8a is 7a. And -6 minus 8 is -14. Divide by 2, divide by 7, you get a equals -2. So what that means is if we were to plug in -2 for a right there and for a right there, that would make these two pieces meet up at the breakpoint. The left and right limits would be equal. I'll take one last one, similar to this one, except this time there's 3 pieces to it and 2 breakpoints. So this time it says find the values of b and c, and b and c are constants, not variables. We're just trying to figure out what they are. So the function is continuous on negative to infinity. And again, you can see the only thing that might make this discontinuous is the breakpoints. This is just a linear one, straight line, a quadratic one, a parabola, and a cubic graph. So this time there's 2 breakpoints, so we have to set the same thing at -2, our first breakpoint, the limit as x approaches -2 from the left of f of x has to equal the limit as x approaches -2 from the right of f of x. So you plug in -2 into from the left, that's the top piece, to where x is less than -2, that'd be c times -2 plus 3b equals -2 from the right. F of x, you'd have to plug in -2 into this piece. So it'd be b times -2 squared minus 4. So c times -2 is -2c plus 3b equals -2 squared is 4 times b, 4b minus 4. Subtract the 4b over. We get -2c. Oops. The b's don't cancel off, so there's one more room there. -2c, 3b minus 4b is -b equals -1. But you can see that's not enough to solve because we've got 2 unknowns and only 1 equation. So our other equation is going to come from using the other breakpoint. So the limit as x approaches 3 from the left of f of x has to equal the limit as x approaches 3 from the right of f of x. So 3 from the left, you'd use this middle piece. That's all where x is less than 3. So it'd be b times 3 squared minus 4 equals 3 from the right. You'd use the bottom piece. That'd be c times 3 cubed minus b times 3. So 3 squared is 9 times b, 9b minus 4 equals So b cubed is 27 times c, so we get 27c, and then negative b times 3 is negative 3b. And so we move all the terms over to one side. If we just subtract the 9b, we get negative 4 equals 27c minus 12b. Now, from here, we've got two different methods we can use algebraically to solve. We've got two equations and two variables, so we can either solve it by substitution or elimination. Now, this one wouldn't be too bad with substitution because it's pretty easy to isolate this b without having to use any fractions. But in general, these tend to be easier to use elimination, so that's what I'm going to do here. You can eliminate the c's or the b's. You can see the c's, you have 2 and 27. B's, you have 1 and 12, so the b's are probably a little bit easier. We just multiply this whole equation by negative 12, and we get a positive 12b that will cancel all of this. So we have to multiply the whole equation by it, and I'm just going to flip the side so that everything lines up correctly. So negative 4 times negative 12 is 48. I'll put that on the left side. Equals negative 12 times negative 2c is 24c. And then negative 12 times negative b is positive 12b. Add those together. Negative 4 plus 48 is 44. 27 plus 24c is 51c. Divide by 51. Gives us c equals 44 over 51. And now if you just solve for b, you can substitute in any of these equations that have b and c in it, but the easiest way is probably right here, because the b is almost by itself already. So if we substitute in there, we have negative 2 times c, we just figured out, is 44 over 51. Then minus b is what we're solving for, equals negative 4. So negative 2 times 44 is negative 88 over 51. Minus b equals, if we get a common denominator, multiply this one by 51 over 51. That's negative, well, 50 times 4 is 200. And then 1 times 4 is 4, so that'd be negative 204 over 51. And then if we just get the b by itself, add the b over here, and add the 204 over 51. Let's see, negative 88 over 51, and then we got 204 over 51, so 204 over 51 minus 88 is 116 over 51 equals, now this is a positive b over here, so that equals b. So that's our solution for b and c. So you can get some fractions on these oftentimes. And that means if we plug those values in for b and c in these different equations, that this would meet up at both breakpoints. And that concludes the notes for AP Calculus on the topic of continuity.